All right, good morning, everyone. Hope you all are doing fine. It's the 14th of November. Let's have a look at our calendar here. We're going to finish chapter 5 today. Yeah, sorry, we're gonna finish chapter 5 today. There's just a couple more things we have to do in there, and then we should have some time to review, at least a little bit of time to review today, and then exam 4 will open on Monday, right? And so uh, the department is doing a couple of reviews for you guys. So if you look over here in the announcements, I think I put in a couple of announcements maybe about a week ago about that. Let's see, yep, right here. Um, so I think there's one today maybe, and then one on Monday that you can go to if you have the time and are available. So yeah, tonight at 6 to 8. They'll have one, and then on Monday, another one, 6 to 8. These are over at the Taylorsville campus. So feel free to go to those if you can. And then I also made a review recording for some online students. And so you can watch that as well. And then definitely you'll want to look through some of these questions, practice problems in these documents down here at the bottom. Okay, so are there any questions you guys want to go over before we get back into chapter 5 here? Anything you're
Can
wondering
we
about? Yeah.
can we just do a brief summary of what we went over in the beginning of 5.7 last class?
Sure. Yeah. So yeah, let's just kind of roll scroll through the notes for a little bit. And yeah, so 5.7 is our return to statistics. 5.6 and 5.5 were both probability sections, and 5.4, I believe. And so what we're doing here is we're coming back to confidence intervals and hypothesis testing. So it's inference. We're taking a sample and we're trying to make a statement about a population proportion. And so we've done that before. What's new about this section? Well, now it's a difference of two proportions. So we're trying to see if one population is different than another population, and if it is, how big is the difference? Okay, so um, and the data structure is categorical variable for an explanatory variable, and another categorical variable for the response variable. So we did one example, so we're just starting with 5.7. There's more to do here. And we were looking at the relationship between gender and uh, body mass index. Okay, so the explanatory variable here would be gender, right? So we have gender as the explanatory variable, so that's a category. And we're looking to see if that has a relationship, an association with being normal weight or not. So we define normal weight as 20 to 25 for a BMI. So either you're of normal weight or not, right? So so normal weight, and this is a yes or a no. So it's also a category. So so the way we do that is we take a sample from two different populations, right? So we had the population of females and we had the population of males, right? So we took a sample from both and we compared the incidence, the proportion between the two populations. Okay, and we built a confidence interval to do that. So this confidence interval is saying, yeah, there is a difference between the females and males, and the females are they have a higher proportion of people who are of normal weight. It could be as low as 5% more, or it could be as high as maybe 13% more. Okay, so that's pretty much what we did in 3.7 last time. And so let's continue with that. Let's look at another example, unless there's more questions. Here, it's the same data structure. We're going to look at a categorical explanatory variable and a categorical response variable. Okay, and so this is an interesting study. You can read more about this. This is so you can download this paper and read about it. What they were doing is they were trying to see if their techniques for investigating and observing penguins is actually causing harm to the penguins, right? So you can imagine back in the day when they were doing wildlife biology and they were observing animals, right? They would use a metal band. Okay, so you're down there in Antarctica and you want to observe penguins for a few different seasons. How do you keep track of them? Well, you put a metal band on one of their flippers, right? So you catch the penguin, you attach a metal band, and then you release it, and then you can identify the penguin later, right? So really interesting work that they're doing there. But they were always wondering, maybe these metal bands are actually detrimental to the penguins. Seems reasonable, right? It certainly wouldn't help to have a metal band on the flipper, but maybe it's not harming them at all, right? So that's what they were trying to figure out. Do we need to get rid of this old technology and just move on to the new technology, which is RFID chips? So with an RFID chip, you can follow the penguin. You just insert that little chip into their body, and then you can follow it, right, electronically. But I imagine for this sort of work, if you can still use metal bands, if they're not harming the penguin, it's still nice to have that as an option, right? So that's what they were trying to figure out. Should we get rid of these metal bands or not? So how would you figure something like that out? Okay, and what kind of experiment are they running here? So they've got an explanatory variable. So that would be the metal band. Okay, does the metal band, is it associated with, or does it cause a lower rate of survival? Okay, so the metal band, it's a yes or no, so it's categorical, and then they're going to follow these penguins for 4.5 years, and either the penguin is alive or not at the end of the 4.5 years, right? So it's also categorical. Okay, so it's chapter 5. That's what the chapter 5 is all about. Okay, so how did they do this? Well, they caught 20 penguins. Okay, so there's a sample of 20 penguins, and they randomly assigned 10 to receive a metal band and 10 to not receive a metal band. So the group not receiving the metal band is our control group. We need that because without that control group, we don't really know what a typical survival rate would be for penguins, right? So if you don't have that control group, you don't really know if the survival rate is low for these metal band penguins, right? So, right, because 4.5 years is kind of a long time, I would imagine, for penguins. So some of them might just pass away because 4.5 years is quite a long time for penguins. So so let's see, what were the results? So they randomly assigned 10 of them to get the metal band and 10 to not, and then they just looked to see how many were alive at the end of the study. And so because it's two categorical variables, we can set up a contingency table. So the row variable is the response variable, and then the column variable is the explanatory variable. Okay, so so what were the results? So there were 20 total, and then so let's read through here. So it says researchers kept track of the ones that survived. They found that 9 of the 20 penguins survived. Okay, so that's over here in the margin, we can put 9. And pretty much every time you get a number, you can use addition or subtraction to find another number or two. So if there's 9 here and there's 20 here, there must be 11 there, right? So that means 11 died during the 4.5 years. Okay, then what else do we know? 3 of these survivors had a metal band. So among the survivors, we have 3 in the metal band group. And then again, we can fill in another cell or two here. If this is 3 and that's 9, this must be 6, right? So 6 of the survivors did not have a metal band. And then I believe we can fill out the next row. If there's 10 here and 6 here, that means 4 without the metal band didn't survive. And then if there's 3 here and 10 here, that means 7 is there. Right? So we have our table filled in, and we know from our earlier study of contingency tables, if we do a conditional distribution, then we can start to get a read on the relationship between the two variables. Okay, so what's the probability they survived given no metal band? Okay, so if we know that they were in the no metal band group, well, there were 6 survivors out of 10 for a 60% success rate or survival rate for the penguins without the metal band. So that was our control group, right? That's our baseline. Gives us an idea of what percent of penguins would survive a 4.5-year time period, right? Just kind of like, naturally out in nature, right? Without any effects from humans there. Okay, about 60%. Okay, it could be higher, could be lower if we looked at the population, but it's a nice idea, a nice baseline comparison. What about the percent or the proportion, the probability of surviving with the metal band? Well, if we know they had a metal band, then they're in that group, which is 3 out of 10, which is a 30% survival rate. Okay, so what we're trying to get at here is well, we know that without a metal band, right? So if I say PNB, that would be the proportion of all penguins. So you have to, it's a bit of a thought experiment. You have to imagine all penguins, okay? And if all penguins didn't receive the metal band, what proportion of them would be alive after 4.5 years? That's what PNB would be. We don't know what that is because, we can't study all penguins in the world, right? So our best bet, or the only option we have here is to estimate it with a sample, right? So that's what we have here. This is P hat NB, the sample proportion of survivors without the metal band. Okay. Then the other thing you have to imagine is, okay, take all penguins in the world and give each and every one of them a metal band on their flipper, right? What percentage of those would survive the 4.5 years? That's what PMB would be. Of course, we don't know what that is because we can't run this experiment on every penguin, right? So the best we can do is take a sample and estimate it with the sample. So this would be P hat MB for metal band. Okay. So to figure out if the metal band technology is bad for the penguins, we would look at the difference between these two parameters over here, right? So what we really want to do is go P no metal band minus PMB. And if there's any difference between those, then that means the metal band is, harming the penguins basically, right? But again, we don't know those two numbers, so the best we can do is subtract the two sample proportions. Okay, so that would be 0.6 minus 0.3, which is 0.3. Okay, so the difference between those two sample proportions is 30%. Okay, so is that significant? Well, it looks like a big difference, right? But who knows? Maybe if we did this experiment again, we would get a smaller number for this and a larger number for this, right? Just because of sampling error, right? And if that were to happen, then this number would be smaller. And in fact, it might even flip and go negative, right? So we don't know, right? Without a distribution, we don't know if that difference is significant or not. Okay, so it turns out we can use the normal distribution to do this. Okay, so if certain conditions are met, P hat NB is normally distributed, and if certain conditions are met, then P hat NB is normally distributed. And from mathematical statistics, we know that a difference between two normally distributed variables is also normally distributed. So in other words, we can use the normal distribution here if certain conditions are met. So what are the conditions? The conditions are here on your formula card. So this box down here is the major set of formulas and ideas for chapter 4. Okay, so we have 4 conditions for chapter 5. So for your exam next week, this is the big chapter 5 section. And while I'm thinking about it, this is also, the other half of chapter 5, right? So make sure you have those on your formula card for the exam, and always make sure you include that too. Anyway, back to this. So we have these 4 conditions that have to be met. And if you look at those, briefly, you'll see, hey, these are actually very similar to what we've done before. Right? We have randomness, we need independent observations, we need at least 10 successes and at least 10 failures, and then we need the 2 samples to be non-overlapping. Okay, so nothing too new there. Let me skip that for now. I want to practice with the technology a little bit, with the software, and we'll calculate our confidence interval. We'll think about what it means, and then we'll go back and think about the requirements and if they've been met or not. Okay, so let's jump into the software here and actually calculate our confidence interval. Let me know if you have any questions here. Okay, so let's open up GeoGebra. Okay, so we go to the toggle, the 3 dots, and then we're down here at the probability calculator. We've been here dozens of times now. Okay, and then you go over to statistics, and then you come down here to the drop down. Okay, so here at the end of chapter 5, by the end of chapter 5, we've gone through so many, over the course of these first 5 chapters, we've gone through many of these inference procedures. So I always do kind of a process of elimination. What is it that we're working on here? Are we doing a confidence interval or a hypothesis test? A confidence interval, right? So it's an estimate. And then we think about the kind of data we have. Well, as I pointed out, this is all categorical stuff. It's, survive or not, metal band or no metal band, right? So it's a proportion. So it's got to be one of these 2, and it's a difference of proportions because it's 2 different populations that we're comparing, right? Okay, so then the confidence level is 95%. Okay, and then we put in our information. So which group is which? Well, it kind of doesn't matter. The numbers will superficially be different, but really they'll be meaning the same thing. They'll just be different by a negative sign. So I tend to like positive numbers more than negative numbers for doing calculations. So I'll put in the no metal band group for my first group. So there were 6 out of 10 successes there. And then for the metal band group, there were 3 out of 10 successes there. Okay. So it calculates the z-score for that sample difference. Okay. And then it uses the z-score to get the margin of error. So we see a margin of error here of about 42%. That's a very wide margin of error. The point estimate is 0.3, so 30% difference for the point estimate. And then we have a lower limit of negative 0.1158 and positive 0.7158. Okay. Please let me know if you're having any questions here about this. So let's write those numbers down. It's telling us that the interval is ranging from negative 0.1158 all the way to 0.7158. Okay, so about negative 12% all the way up to 72%. So it's a huge interval, right? So we've computed it. Let's interpret it now and see what we think about this. So there's 95% confidence that the interval captures the difference between proportions. Okay, so the two proportions are or are not significantly different. Well, let's think about what this interval is doing. Okay, it's trying to capture this difference between the 2 survival rates, right? So let me give you kind of a silly interval first. It's got to be between -1 and 1, right? Because these are proportions. So the least it could be is if all of the no metal band penguins died and all of the metal band penguins survived. That would give us -1. Okay. The other extreme would be if all of the no metal band group survived and none of the metal band groups survived. That would give us 1. But those are really extreme, right? So probably what's going to happen is somewhere in between, right? So there's 0 in the middle, and we got 0.3 for our point estimate, right? So 0.3 is about right there. Okay, so we're trying to capture PNB minus PNB. Okay, it's somewhere in here, right? So we have our 0.3 in the middle, and then we add a margin of error on the right, and we add a margin of error on the left, right? So it's the same margin of error on both sides. So 1 on the left, 1 on the right over there, and then 1 on the left over here. Okay, so that sets up an interval ranging from negative 0.1158 up to 0.7158. Okay, so what this interval creates is a list, basically a set of plausible values for the difference between these two parameters. Okay, so are they significantly different? Well, that comes down to 0. Is 0 in that interval or not? Well, 0 is in the interval, right? Because the left endpoint is negative, the right endpoint is positive. So that means 0 is included in the interval. 0 is a possible, we're not saying it's equal to 0, but it could be the case that PNB minus PNB is equal to 0. And if the difference between them is 0, then they are not significantly different. Okay? So, you know, if you're a researcher and you've been working with these penguins and maybe you have a good feel for what these metal bands are doing, you might believe that they actually are harming the penguins, right? Or you may not. But let's imagine you still believe it. You can still believe it, but this data set doesn't prove that the metal bands are harming the penguins, okay? Because it's possible that the difference between those two parameters is 0, okay? So does that make sense? Okay, so again, it could be that metal bands are bad for the penguins, but this data set does not prove that. Okay, this data set does not prove that there's a statistically significant difference in survival rates between the two groups. Okay.
And that's because it contains 0.
Yep, exactly. Exactly. Good. All right, so let's then there's a couple of other things down here. So if 0 is inside the interval, it means that the data does not prove that we have a statistically significant difference. Okay, so if 0 is in there, it's still possible that there's no difference. Okay, so maybe there is a difference, but that particular data set doesn't prove it. If 0 is outside the interval, it means that the two proportions are significantly different. Okay, because if 0 is not in the interval, 0 is not a possible value for the difference. Okay, and then if the entire interval is negative, then P1 is smaller than P2. If the entire interval is positive, then P1 is larger than P2. But we don't have that case here because we had 0 inside the interval. Let's critique this study a little bit. Okay, so one thing I didn't do here was check the conditions before we started, and that's not a good practice. You really should check your conditions before doing the inference procedure. So let's go through these. So again, these are from your formula card, and they should be very familiar to you. We've used stuff like, well, let me just scroll up here to chapter 3 and remind you guys, it's very similar to what we had in chapter 3, right? We had randomness, we had independence, we had at least 10 successes, at least 10 failures, right? So it resembles chapter 3 quite closely there. There is a fourth one because of the additional sample. We have 2 samples, right? Okay, so let's go through those and make sure these are all met. So do we have random samples? Yes, in fact, it was a randomized experiment, wasn't it? Okay, so the 2 penguins were randomly, I'm sorry, all of the penguins were randomly assigned to either get a metal band or not. So we do have the principle of randomness there. Okay, the second thing we have to check is that we have independent observations. Okay, so there's two kinds of independence here, right? So it says independent, it says independent. What does it mean? Well, the first kind of independence is within sample independence. Okay, so what does that mean? Well, among the penguins not getting the metal band, we want those penguins to be independent of each other. We don't want them to all be from the same, extended penguin family or something, right? We want them to be randomly selected from across all penguins. Okay, so the rule of thumb, just like it was in chapter 3, is that the sample size has to be less than or equal to 5% of the population size. If that holds, then there's a really good chance that the penguins in the sample are unrelated to each other. Okay, so that sample size, remember, was 10. So let's just put the 10 in there like that. So that should be 200, right? Are there more than 200 penguins? Yeah, absolutely. Now, why does it have two of these? Sorry, I'm looking at the wrong thing. Why does it have this thing written twice here? Well, because there's two samples, right? So this would be for the penguins without the metal band. This would be for the penguins with the metal band. But because both of the sample sizes are 10, the calculations are identical. So I only have to do that once. If we did it again, it would be the same exact number, right? So we don't have to do that twice here. The third requirement is that the samples are large enough. Okay, and the rule of thumb is as long as you have about 10 successes and at least 10 failures, you should be good. It should be large enough for the central limit theorem to work. Okay, so we have to check two things. N1 P1 hat has got to be greater than or equal to 10, and then N1 P1 hat, N1 times 1 minus that also has to be at least 10. Okay. All right. So the subscripts here. Hopefully that's not confusing. What is the 1 there? That's just no metal band, right? So if you prefer, we can say, like N there for no metal band. It gets kind of complicated. I almost prefer using a 1 there. But anyway, just to distinguish those two groups. Now, they both have size 10, right? Sample size 10. So, and then what else? What is this saying? This is saying the number of successes, right? So among the metal band group, there were 6 survivors. And how many failures? 4 failures, right? 4 that did not survive. Notice that these are false, right? 6 is not more than 10. 4 is also not greater than or equal to 10. So what does that mean? Well, it means that there's a flaw here with the study. Okay, so the conditions here have not been met. The samples are too small. That's why that interval was so wide, right? I mean, it had a margin of error of like 30%. Okay, and so it's a flawed study. They really need to have more penguins in this study for us to be able to get a solid inference. Okay, so at this point, there's two things we could do. We could just say, well, the whole thing is junk, and we're going to throw it out and ignore it. Probably a more prudent approach would be to say, well, okay, collecting data on penguins is difficult, right? You have to go to Antarctica at least a couple of times, right? And do that. And the number of people who know how to do that is very small. It's expensive. So, we're not going to throw the data out. We'll go ahead and use the confidence interval, but we're going to, just tell people, hey, we're a little bit unsure of the results here. Okay, so it's kind of like an asterisk, right? So so on the exam, if you see that, just point that out. Just say the conditions are not met. Go ahead and go forward with the analysis, and just say, this is what we would typically, say with this confidence interval, but we're a little bit unsure in the results. Okay. Now, later I'll show you a technique based on randomization basically coin flipping that has no problem with small samples. Okay, so this distribution problem here, we can solve it by using a different technique. Okay, and we'll talk about that later. But for now, we just do the analysis and we just say, hey, the conditions weren't met, so we're going to be a little bit cautious of the results. Okay. Any questions there about that? So you guys try one. Okay. So heart transplants, really wonderful technology and medical procedure that we have. So if you have heart failure, then if there's a donor available, donor heart, right, you might be able to get a heart transplant and then live longer, right? But at some point, they didn't have these, right? If you go back far enough in time, back towards, I think it was maybe like in about the middle of the 20th century when they started doing these more. So if you go back like 100 years ago, they didn't really do this very much or at all. So how did, back then, how did they know that, or, when they first started with this procedure, how did they know it worked, right? Well, they did studies, right? And they built, they did hypothesis tests and confidence intervals. And one of these studies was done by Stanford University. Okay, so it's called the Stanford University Heart Transplant Study, and it was quite an experiment that they did. They had volunteers, and probably they were patients who were, at risk for cardiac events, right? And basically they volunteered and they said, okay, yeah, if I have heart failure, then I want to be a part of this experiment. And they knew that some of the people in the experiment would be part of the control, right? So they said, okay, well, if I'm in the control, I'm in the control. I don't get a heart transplant. If I'm in the treatment, then I get a new heart, right? And they were willing to do this, so that was quite nice of them. There were 69 who received a transplant, 24 of them survived, and then there were 34 in the control, 4 of those survived. Okay, and again, we really need that control group because without the control group, we don't really have a great idea of what the normal survival rate would be, right? If nature took its course, right? So we've got the control group, and that'll serve as a baseline, and then we have our treatment group. So the explanatory variable here is new heart, right? So the explanatory variable is, did they get a new heart? Yes or no? So that's categorical. And then we're looking to see if that causes a higher survival rate. Okay, or survival, right, for somebody. So survival is a yes or no thing, right? Either you survive for some time period after the transplant or you don't. So it's also a yes or no. So it's chapter 5, right? 2 categorical variables, right? And then so I want you to calculate and interpret a 95% confidence interval for the difference between the proportions. And these proportions are survival rates, right? So survival for those who received a transplant and those who didn't, okay? And then are the proportions significantly different? If there is a difference, which is bigger, P transplant or P no transplant? Okay, so I'll go quiet for a few minutes and let you guys try this. It's basically identical to our last problem, just different context and the numbers are different. Okay, so I'll give you guys about let's do 5 minutes on this, and then at 12:09 we'll come back together and talk about this. Okay, so get going on this and see what you think the difference is between these two populations. All right, let's come back together on this. So we've got two groups again. We have the group that received the new heart. So we can call that sample 1. There were 24 successes. There were 69 in that group. And so that gives us a success rate, survival rate of 24 over 69, which is about 0.3478. It's about 35% success rate among the group that got the heart transplant. Among those who did not receive the new heart, there were 4 successes out of 34 for a success rate, and it's just it's a sample proportion. It's not the population. It's 4 out of 34, which is about 12%. So there are people who have some kind of cardiac event, maybe like a very serious event, who can still survive. Okay, it's not very common, but it does happen. So that gives us a nice baseline to compare, the success rate among the transplant group, right? So what is it that we're interested in? It's actually the difference of those two statistics, right? So what we'll do is we'll go P1 hat minus P2 hat. So that's 0.3478 minus 0.1176. Okay, so if we subtract those, let's see here. It's going to give us 0.3478 minus 0.1176. So about a 23% difference. Okay, but again, this is based on 2 samples, and samples have sampling error, and it's entirely possible that if they did this study again, that this number would be lower and this number might be higher, right? And if that's the case, then the difference would be smaller. It might go to 0 or it might go negative. I mean, I don't think it would go negative, but who knows? Maybe, back when before they did a lot of heart transplants, they might have thought, well, it might make it worse, right? If you take somebody's heart out, it so so yeah, who knows if it's actually better, right? So that's what the confidence interval will do, is it will help us estimate the difference of the 2 parameters. So really what we want is this P1 minus P2, but we never really know exactly what that is because we can't give everybody a heart transplant. Um, so what is that interval? Did anybody get the interval by any chance? The left endpoint, right endpoint. Let's see, Killian. Oh, Killian's asking me a question here. Will P1 always be greater than P2? Good. No, P1 might be smaller than P2. And so what I typically do is I typically like to work with positive numbers instead of negative numbers when I can. So I just I just sort of look ahead in the problem a little bit. And I just say, well, which one is more than the other? And the one that's larger, I'll usually let that be the first sample. But well, if I remember to do it, we'll actually switch that order at the end, and we'll see if we get equivalent results. The numbers are cosmetically different because they'll have like a negative sign, but it all has the same interpretation. Does that make sense, Killian? So great. Brock and Shoshana have the correct interval here. So 0.0741, and then we're going up to 0.3862. Good. So 0 is not in that interval, okay? So 0 is not a plausible value for the difference between the 2 parameters, okay? So that means heart transplants do help, okay? So they do help, and so that's a useful thing that the confidence interval tells us. The other nice thing is it estimates how helpful it is, right? If it was helpful, but it only helped by like 0.5%, then it might not be worth doing, right? But if it helps, you know, like if it gives like a 10% increase or even like a 7% increase, that's great, right? And it could be as much as 39%. So that's good, right? All right. So it was basically statistics like this that well, statistics like this played an important role in establishing this the importance of and the acceptance of doing these heart transplants, right? And for getting donors, willing to do this, you can show them, look, this really does help, right? So good stuff here. So are the proportions significantly different? Yes, they're different. And we can tell they're different because 0 is not in the interval. And then if you look at the interval, it consists entirely of positive numbers. So that means the proportion of survivors getting the transplant, I'm sorry, the proportion of people getting the transplant who survive is higher than the proportion um, who don't get the transplant and survive, right? So good. Now let's be a little bit critical here and think about the requirements. We didn't really check those requirements, did we? So let's go back to the list again, right? So we have these 4 things we have to check. And unfortunately, I think we see a similar problem with this experiment. Okay, so they were randomly assigned to get a heart transplant or not. So this is for the Stanford Heart Study. Okay, so we had randomized experiment. Okay, so that was fine. 2, I do believe we have independent observations. So the people, so that's within sample independence. So the 69 people who got the transplant, that's a very small number compared to everybody with cardiac, who's at risk for cardiac event, right? So yes, 69 was the sample size for the first group. That should definitely be less than 5% of all people with heart issues, right? So if we divide by the 0.05, that should be fine. So 69 divided by 0.05. So yeah, 1380. Yeah, certainly there's more than 1,380 people who are at risk for a heart attack, right? So should be fine there. And then with the other sample, it's even, it's obviously the case, right, that 24, 24 being less than 69 must be less than 5% of the population, right? So we're good there. But again, I think we're gonna fail here on the 3rd requirement, right? So we need to have at least 10 successes and at least 10 failures in both groups. So among the transplant group, okay, so among the group getting the transplant, how many successes were there? There were 24 successes. That's more than 10. And so if there were 69 people getting the transplant and 24 of them survived, that means there were 45 who did not survive, right? So we had enough in the transplant group. Unfortunately, I don't think there were enough in the non-transplant group. Okay, how many successes were in the non-transplant group? There were 4. 4 is not more than 10. Okay, so this 3rd requirement again is not met. Okay, so what do we do with that? Well, unfortunately, we have to put kind of an asterisk next to the results. Okay, so do we have to throw it out entirely? No, but it's not really going to be a conclusive result here for us. Okay, so And you know, it's one of those things you learn as a researcher. You want to make sure that before you start with the research, you have you know, you're going to be able to meet all of the conditions at the end of the study, right? So if you're going to use the normal distribution, you need a larger sample. But it turns out there's another way, and it's using our randomization applet. We'll talk about that later. That's basically kind of a fix for this. Okay, so if you do have a small sample, you can still do inference. Okay, but anyway, so what would we say here? We would say the conditions are not met. We would go forward with the analysis, and just at the end, we would say that it's somewhat questionable, the results. Okay, because again, these kinds of data sets are hard to put together, right? I mean, think about an experiment where people are getting heart transplants. That's very costly, right? So we don't want to throw the data out or completely ignore it, but we do, if we're being honest, we do have to be a little bit extra skeptical of the results. So that's it for the confidence interval stuff here. Are there any questions about that? So we know now how to build confidence intervals for comparing two populations when it comes to a categorical variable. Now what we're going to do is the other major kind of inference, and that's hypothesis testing. Okay. So unless there's questions, I'm going to just keep moving on here. We've been doing hypothesis testing since chapter 2. And every chapter since then, we've had a new kind of hypothesis test. And so that's good. By the time you get to chapter 5, the hypothesis test idea should be pretty easy for you to follow, I think. Okay, so it's the same hypothesis test, but different data, right? And so I think what you'll find is that you'll pick it up pretty quickly, all right? And so there is some theory here that we're going to talk about. Checking the conditions is a little bit more complicated, but the basic idea I think will make a lot of sense to you. So the one thing that is a little bit different is this idea of the pooled proportion. Okay, and so under the null hypothesis, what we'll see is that that there is no difference, right? The null hypothesis is that there is no difference between the two populations. Okay, so if the two populations are coming from the same, if they're basically coming from the same population, then the two proportions will equal each other. P1 will equal P2. Okay, and then so if they're coming from the same, if they have the same proportion, then we should be able to blend the two together to get our estimate for the population proportion. Okay, so this is what's called the pooled population. So we're going to take the number of successes from the first sample plus the number of successes from the second sample, and we're going to divide by the sum of the two sample sizes. So it's like an average or blended success rate. Okay, and so there's two versions to this formula. This is the formula on the formula card, and I think it's easier, much easier to use than this one. Okay, so they're equivalent, but the one on the right is just easier. So I just always use this one. Why do we need that? Well, it's for checking the conditions. So we're at the two sample z-test for difference of proportions, and what we have to do is make sure we're expecting under the null at least 10 successes and at least 10 failures. It's very similar to what we did in chapter 3. Okay, remember in chapter 3 when we were looking at single proportion hypothesis tests, we had to have at least be expecting under the null at least 10 successes and at least 10 failures. Well, with the hypothesis testing, remember, it's different than the confidence interval. With the confidence interval, it's p hat. With the hypothesis test, it's p0. It's the null value for the proportion. In chapter 3, that wasn't too bad. P0 was simply the number on the other side of the the null hypothesis equation. But when it comes to two-sample hypothesis testing, we don't actually have a P0. So what we need is an estimate for P0, and the best we can do is this pool proportion. Okay, so that's a lot of talking. Let's actually just practice with one of these pool proportions. Okay, so back to the heart transplant study. If we were to do a hypothesis test for that, what would that look like? What would the pooled proportion be? Okay, so the pooled proportion, p hat, is the number of successes from the two samples added together divided by the sum of the two sample sizes. Okay, so how many successes did we have in the first sample? Well, there were 24 who survived out of 69. Okay, and then in the second sample, there were 4 who survived. And what was the sample size in the second group? 34. Okay, so it's going to be 28 over 103 for a pooled proportion of about 0.272. Okay, so that's our pooled proportion, and we're going to use it in the next problem. Okay, so I just wanted to have one problem in here where we practice with pooled proportion, and then we can actually use it in our first hypothesis test over here. Okay, so I want to skip this class activity for now, come back to it later, and I want to jump right into a hypothesis test. Okay, so let's return to our penguin data and think about how the hypothesis test would look. Okay, so there's a lot here that's the same as before. We have the same two competing hypotheses. We have the null, kind of skeptics, boring hypothesis of no difference. So it's the hypothesis of equality, right, between, well, the equal sign. And then we have the alternative hypothesis, which is the hypothesis of some difference. So instead of an equal sign, we'll see some kind of inequality, right? We'll see a greater than, we'll see a less than, we'll see a not equals. Okay, and we call that the researcher's hypothesis because if there's a difference, if you establish there's a difference, then the next step would be to explain why there's a difference, right? It would require further research. If they're equal, then there's nothing really left to study. It's fine if they're equal, but it's not necessarily a bad thing. It's just that there's nothing else to study. Okay, and so so that's the same as before. What's different? Well, now our parameter is p because we're looking at proportions. We've seen that before, so what's different? Well, we have p for our first population, and then we have the proportion for our second population. Okay, so the skeptic will say, all right, you want to get rid of these metal bands. Okay, fine, but you know, we've been using these, you know, and we've done a lot of important research with them, and you know, we still have them, and you know, we can still use them. So I'm gonna just assume that they work until you prove otherwise, right? And then the researcher comes along and says, no, we're pretty sure that the group without the metal band is surviving at a higher rate than the metal band group, right? In other words, the metal bands are actually causing problems for the penguins. So we want to stop using them. Okay. So does that make sense? And why are we doing a one-tailed test here instead of a two-tailed? Two-tailed is kind of our default. Well, you know, I just don't think there's any reason why you could come up with, you know, a possibility where the metal band group would do better than the no metal band group, right? So I think there is just sort of a really good reason to only do a one-tailed test here instead of two-tailed. Again, because I just can't ever imagine any case where penguins with metal bands are going to have a higher survival rate than no metal band. Okay. All right. So we write out the hypotheses, and then we check our conditions. Let me put that on pause for a little bit. I want to run through this software so you can see how this works, and you can see, oh yeah, it's very similar to what we've done before. To do this with the software, we would come over here to GeoGebra. Let me refresh this. So we'll hit the toggle, the 3 dots, probability calculator. Okay, we go over to statistics, and then we come down to our drop-down menu. So what is it that we're doing? Well, we're doing a hypothesis test. We're not doing an estimate. Estimates are confidence intervals, right? So we're up here, okay, and then we think about the kind of data we have. These are categorical variables, right, which means we're looking at proportions, not means. Okay, so we're one of these two here, and because it's two different populations we're looking at, it's a difference of proportions. So the null is already set up as 0, right? The alternative is that the first group does better than the second group. Okay, and then so we put the data back in, right? So there were 6 out of 10 surviving in the no metal band group. There were 3 out of 10 surviving, and there we go. Okay, so GeoGebra calculates it for us. By the way, what is it calculating? It's here on your formula card. If you want to do this by hand, you can. I forgot to point this out for the confidence interval. There's a formula for the test statistic. Oh, whoops, I'm looking at the wrong section, aren't I? It's right here. There's a formula for the test statistic. It's a z-score. Okay, so we look at the difference in the 2-point estimates minus the difference in the null values, and then we divide by the standard deviation, an average standard deviation. So it's a z-score. Okay, so it calculates a z-score, then it looks in the normal distribution, and it calculates a p-value for us, right? So we have our z-score, we have our p-value, very similar to other hypothesis tests that we've done. Let's write those numbers down and see what our conclusion is. So the test statistic here is a z-score. Pretty much in this class, anytime we're working with proportions, we have a z-score, and the p-value here is 0.08888. All right, so this part is pretty easy. We take the p-value, we compare it to alpha. P-value here is more than alpha. Since the p-value is more than alpha, we do not reject the null. Okay, so the null is that the bands are not harming the penguins, right? When we do not reject, we're not rejecting because the evidence is insufficient. Right, so there's insufficient evidence to conclude that the survival rate among the no band group is higher than the survival rate among the banded group, right? So, so in other words, we would say to conclude that penguins without metal bands have higher survival rate. Penguins with bands. Okay, so you might, as a researcher, still believe in your heart that these bands are causing problems for the penguins, but this data set doesn't prove it. Right, so there's insufficient evidence to conclude that penguins without metal bands have a higher survival rate than penguins with the bands. It's still possible that there's no difference between the two. Let's do a couple of other things here. Let's look a little bit deeper in at the p-value, and then we'll think about our conditions. Okay, so one way of interpreting a p-value is to think of it as a repeated experiment. Okay, so let's say we're all independent penguin researchers, right? So I have my own penguin research, and then each of you have your own projects, and we're actually all studying the same thing, but individually. Okay, so I go down there and I get my sample of 20 penguins, and I run this survey, this experiment, right? And then each of you does it, right? In fact, let's say there's 100 of us, and we have 100 repetitions of this experiment. Okay, what this p-value means is, well, it's the the likelihood, right, assuming that the null is true, so if the null is true, if there's no difference between the groups, then we have about a 9% chance of getting that the difference we got are more extreme, right? So if we took that p-value and we did this experiment 100 times, that would give us about 8.9. So if the population proportions are equal, if there's no difference between bands and no metal bands, then we would basically get the same sample difference or more, right? We would expect a sample difference in proportions greater than or equal to the one observed in about 9 out of 100 repetitions. So in other words, 9 times out of 100, we would get this difference or more just by chance. And that's why we're not rejecting, because that's not really sufficient to prove that there's a difference between the two groups. Okay, so that's one thing I wanted to do there, was go a little bit deeper on the p-value interpretation. And then let's also check our conditions. Okay, so these conditions are on your formula card, so you'll have these on the exam. And they're very similar to what we've done before. They'll look very familiar to you. Okay, so we need a random sample, right? We need independent observations. Under the null, we need to be expecting about at least 10 failures or at least 10 successes, and we need the two samples to be non-overlapping. Okay, so do we have those conditions met? I don't really have a lot of space on this page, so I'm going to do that over here. So this will be the Penguins hypothesis test. Okay, so first of all, do we have a randomized experiment? Yes, it says it was a randomized experiment. Okay, 2, just going back here to the formula card. Do we have independent observations? I believe so, right? For the first group, there were 10 who did not get the metal band. Okay, and then so if I divide by 0.05, that's 200, right? So we already did this for our confidence interval, right? So, so yeah, there's definitely more than 200 penguins out there. Then 3, we have to make sure that under the null, we're expecting at least 10 successes and at least 10 failures. So for both groups, we need this n1 p hat to be greater than or equal to 10. The p hat, notice there's no subscript there. This is not, it's not p1 hat, it's not p2 hat. This is the pooled proportion. Okay, so it's different than the confidence interval. It's similar, but the numbers will be different. Okay, so n1 is 10. What is p hat? Well, p hat is the blended pooled proportion. So I'm going to go x1 plus x2 over n1 plus n2. Okay, so that's our p hat. All right, so how many successes were there in the first group? There were 6 out of 10 survivors. And then in the second group, the banded group, there were 3 out of 10 survivors. Okay, so that's 9 out of 20, which is a pooled proportion of 0.45. Okay, so that's our p hat. And there's no p1 hat. This isn't p1 hat or p2 hat. This is p hat. This is the blended pooled proportion. Okay, so under the null, our best estimate for the proportion of survivors would be 45%. Okay, so 10 times 0.45 is 0.45. Is 4.5, right? So again, we've seen several examples today of this happening where we do not meet all of the requirements. Okay, and so we'll have to look at another technique later called randomization, basically coin flipping, that will allow us to move forward. So even with small sample sizes, while the normal distribution approach is flawed, we can get around it. Okay, later. Okay. So for now, for these kinds of problems, just want you to point out if it's met or not met. It's not met here. And then we'll still go forward with the calculation and the conclusion, but we'll just kind of have in the back of our minds kind of an asterisk, sort of a bit of a skepticism about the results for now. Later, we'll be able to get around this problem. Okay, we're getting a little bit low on time. This section does take a while because of all of the conditions that have to be met. So in our last 11 minutes here, I want you guys to try one of these problems, okay? So any questions here about this? I think that most of the details will make sense to you pretty quickly because, like I said, this is like our fourth or fifth time through hypothesis testing. So on this one, let's go to a different topic. Let's think about sleep. This is, something we're all thinking about all the time, and we'll read studies about these, in the news. And so it's kind of interesting. It's sleep deprivation. This was done by the CDC, and they were looking at two different populations, Californians and Oregonians. Okay, so folks from California and people from Oregon. And they were looking at the rate of sleep deprivation between these two states. And they want to know, is there a difference between the proportion of people in California who are sleep deprived and the proportion of people in Oregon who are sleep deprived? Okay. And so I want you guys to try this. We don't have a lot of time, so we probably won't be able to check all of the conditions here, but I definitely want you to write out the hypotheses, practice with that. Then I want you to jump into GeoGebra and practice with calculating the p-value and your test statistic and writing out the conclusion. Okay, I think we definitely have enough time to do that. So I'll go quiet for a few minutes, let you guys work through this. If you can, later check the conditions. I have a feeling we're not going to finish that today, but we already did an example of it, so you should be fine. And if you do want to see the answer to that checking the conditions part, just jump into the YouTube channel, right? And you can see that finished there. Okay, so all right, I'll go quiet for a couple of minutes and let you guys work on this, okay? So for the hypotheses here, we'll have the null and the alternative. Okay, and then we have two proportions that we're looking at. We're looking at the proportion of people in Oregon and the proportion of people in California. And so they're basically looking at a state effect, right? You know, is this sleep deprivation, is it different between different states, right? So state is categorical, and then sleep deprivation, you're either sleep deprived or you're not. So that's also categorical, okay? And then so the null is that the two are the same, okay? And then the alternative is that there's a difference between the two. And so is this a right-tailed, left-tailed, or two-tailed? Well, it just says a difference, right? And then so that's kind of the default there. So then we have a significance level in alpha of 0.1. Okay, and then so what are the sample statistics? So in Oregon, there were 413 out of the 4691 who were sleep deprived, so it's about 9%. And then in California, it's a notice that it's a much larger sample, but that's okay. The math is flexible with that. It does not have to be the same size. You have about an 8% sleep deprivation rate. So which do you think I would let be my first sample? Well, when I'm going to GeoGebra, I'd probably let Oregon be the first sample because it's a larger number, right? So if we go p hat Oregon minus p hat California, so that's 0.088 minus 0.08, we're at about less than 1% difference. Okay, so is that really statistically significant? Well, we don't know. This is a very large sample, and we've seen that with very large samples, even small differences can be detected. So, so we're just not sure yet. We really do need to have a distribution and a p-value, right? So if certain conditions are met, and these are the conditions, we don't have time today to prove these, but you know, I did show you how to do this, so you should be able to check those. So if certain conditions are met, then both of these will be normally distributed, which means the difference between them will be normally distributed. Okay, so we can use the z-distribution. So come over here to GeoGebra. Did anybody get a p-value or a test statistic for us here before I show you how to do it? Anybody find the p-value? So we go toggle, 3 dots, probability calculator. We go to statistics, we got the drop down. This is a test, right? So it's not an estimate. So we're going to be up here. So it's going to be z-test difference of proportions. The null is that there's no difference. The alternative here is that there's a two-tailed test, right? So I'm going to use Oregon for my first sample. So there were 413 there out of 4691. Then for California, 924 out of 11,545. Okay, so we see our z-score of 1.68. So it's within 2 standard errors of the null value. So it's not really super unusual. P-value reflects that, right? So it's about 9% chance. And so do we reject or not? Well, it depends on alpha. Okay, so let's write those values down. We have a z-test statistic here of negative, I'm sorry, 1.68, and then the p-value of 0.0925. Okay, so what do we do with that p-value? We compare it to alpha, right? So alpha here is actually a larger significance level, 0.1. The p-value is less than alpha. So since the p-value is less than alpha, we reject the null. Okay, so how would we say that? We would say there is sufficient evidence to support the claim that there is a difference between the sleep deprivation rate in Oregon and the sleep deprivation rate in California. And we call that the researcher's hypothesis because, well, now you have something that you've got to explain, right? Or that you know, as a researcher in that field, that's what you would want to do, right? That's what you're interested in. You want to go about explaining why there are, you know, a higher rate of people in Oregon that are having sleep problems than in California. Okay. All right, so actually it took a little bit longer than I thought, but I still think there's plenty of review options out there for you guys. So as we discussed earlier, right, we've got the video I made for you, and then you've got the two review sessions at the Taylorsville campus. Tuesday, I'm sorry, next Tuesday, I'm more than happy to meet with you and go over any questions you have on this Tuesday here. So. But but just like other other exams, I will leave that class time open for you to go take the exam. So we won't meet on Tuesday. So the next time we'll see each other, we'll be back here on the 21st at the end of week 14 out of 16 weeks. So we're really, you know, getting to the end here. That Thursday we'll start with the last chapter of the semester. Are there any questions here as we break or as we finish up here for the week? Anything I can help you with? All right. Well, then have a good one, guys. Have a nice weekend, and I'll see you guys next Thursday. Take care.